Fine?
Yes, sir.
Yeah. And that is an important difference between this and the Hopkinson. And one more difference is, if you look at the output of generator here, you see, whatever the energy generated by the generator is getting dissipated through a resistor. Correct?
Sir.
Whereas in Hopkinson, like I will show you the circuit diagram, you see, Hopkinson, I'm not dissipating any energy at the output. Instead, I'm giving the energy generated back to the other machine. That's why it's called back-to-back test or regeneration test. That means I'm not wasting energy. But here, I'm wasting energy because I'm dissipating energy across a resistor. Right?
Yes.
Yes, sir.
Oh, okay. So now we will go ahead with the explanation. One machine runs normally as a motor, drives generator, whose output is wasted in a variable load resistor R. So that's very obvious from the diagram. Iron and friction losses of the two machines are made equal. Now here, our intention is to make iron and friction losses of the two machines the same. How it is done? By joining the series field winding of the generator in the motor armature circuit so that both machines are equally excited. Please note, iron friction losses, they become the same for each of the machines only when the field current is the same in each of the two machines. And second point is by running them at equal speed. And these two were not possible in case of Hopkinson because it was very difficult since the two fields were different. But here the fields are in series, therefore we are in a position to satisfy these two requirements. That means one, we make the current through the series field winding are the same. Number two, I can run them at equal speed. The load resistance R is varied till the motor current reaches its full load value indicated by ammeter A1. Please note, like what I'm doing is I'm essentially loading the motor by loading the generator. I repeat, my objective is to load the motor. That is done in turn by loading the generator through an external load resistor. Are you able to get this aspect?
Yes, sir.
Therefore, I'm going to vary R. Okay, that means that the two machines are running at rated speed. It's a common speed. And further, the field current through the two series field windings is the same. In this condition, we are going to vary R such that rated current is passed through the motor. Is it clear? So, till it reaches full load value indicated by ammeter A1. After this adjustment for full load current, ammeter voltmeter readings are noted. So now we will see, let V be the supply voltage. So here, supply voltage for the motor, and I1 is the current taken by the motor. V2, the terminal potential difference of the generator, and I2 is the load current of the generator. Intake of the whole set, that means the total power taken by the entire set, is V into I1, the voltage applied into current through the motor. Please note this is motor, the generator. So the current shown by A1 is the total current taken by the entire set. And the output is V2 into I2, that's across the generator. Therefore, the total losses in the set is input, whatever I'm drawing from the mains, minus the output, which is V2, I2. Are you able to appreciate this? It's okay? Any doubt here?
No, sir. No doubt, sir.
Yeah.
No doubt.
Now, armature and field copper losses for both the machines put together, RA plus 2 RSC. Okay, please note, this is the armature loss of the motor, that is the first machine, RA plus the two series fields are together in the armature circuit. Therefore, 2 RSC into I1, because I1 is the current here. So I1 into 2 RSC plus RA. Of course, here a small mistake is there. This must be I1 square. Correct? I1 square into this plus the copper loss in the second machine, which is generator, I2 squared into RA. Any doubt here?
No doubt,
Okay.
sir.
Yeah.
No doubt.
And here RA is the hot armature resistance of each machine. What is the meaning of hot armature resistance? The resistance of the armature when it is running. Please note, when the machine is put off and it gets cooled, the resistance of the armature will decrease. The moment it starts running, because of the heat developed in the machine, temperature will rise, and because of that, resistance will also rise. Therefore, this RA is a hot armature resistance. Normally, what we do is we measure the armature resistance when it is not running, that is in a cold condition, and we multiply that by 1.4 or 1.5, that gives us the hot armature resistance. Is it fine? Is it clear?
Yes, sir.
Yes, sir.
Okay. Now again, uh, the total losses in the entire set is total power taken from the mines minus the output across the generator, and further the armature and field copper losses for both the machines put together is this RA plus 2 RAC into I1 square plus I square RA. Now, again, please note RSC is also hot series field resistance of each machine. Is it clear? So RSC is also 1.4 or 1.5 times the core resistance value. Then the stray losses for the set is WT, which is the total loss, minus the copper losses. Is it fine? Stray losses for the entire set is total loss minus copper loss. Therefore, stray losses per machine is WT minus WCU divided by 2. Stray losses are equally divided between the machines because their excitation and speed are same. This is important. And this is not possible in case of Hopkinson. That is where Hopkinson becomes slightly inferior compared to this Fields test. Is it clear?
Yes, sir.
Okay. And once we know the stray loss, now we can calculate efficiency for the motor, where the motor input is V1 I1. Again, please note, V1 is across the motor input, V1 into I1. And okay, motor losses, armature and field copper loss plus stray loss. Armature and field copper loss is RA plus RSC into I1 square plus WS is the stray loss. Is it clear? And I can call it as something he has called. I'm not able to see it properly. Can you see what is this? W. Can you see this?
No, sir, it's blur.
Sir, I think WM.
Maybe. So this is the loss of the motor. Now I can write efficiency of the motor. Yeah, as input V1 I1 minus the loss divided by the input. Please note output is input minus loss. And similarly, for generator also I can find the efficiency. Again, generator output is V2 I2. Field copper loss is I1 squared RAC. Armature copper loss I2 square RA. Stray loss, which you have already found from the test, is WS. And total losses I1 squared RC plus I2 squared RA plus WS, again WG. Now efficiency of generation of generator V2 I2, which is the output, divided by output plus loss. Is it clear?
Yes, sir.
Yes, sir.
Yeah.
Yes,
So if you have any doubt, you can ask me.